number 9. I thought I would do number 9 just because it's a cube, and I didn't know if you remember how to factor a cube or not. So we got t cubed minus 8. If I try to do direct substitution to find out what the limit is, and I plug 2 in, what do I get on the bottom? I get 2 minus 2 is 0. So can't do it, right? Have to figure something else out. So the first thing we try when we can't figure something else out is to factor this. And if you remember for a cube, let me go ahead and write, I'm going to keep writing down limit as t approaches 2. And I'm going to try to factor the top. When you have the difference of two cubes, I don't know if you remember this, but if you have a cubed minus b cubed, how you factor that is you take the thing that was cubed, the a, and you subtract the b. So this subtraction sign matches the subtraction sign in the original problem. Okay, so I'm talking about this right here. It matches this. Okay, and then the second, there's another expression that goes with it when you factor, and it's a squared. And then this plus here that I'm going to write is always the opposite of whatever the red sign was over here. So since there was a subtraction sign, a minus b in the first factor, this will be a plus, and then it's ab, and then it's always plus b squared. That was a factoring pattern for cubes, and it's been a while since y'all seen that. I don't know if we've even done it this year. I think in Algebra 2 we do it. All right, so if I want to factor this, this is t cubed. I have t cubed minus 2 cubed, right? So to factor this is going to be, I'm using t and 2, so t minus 2, and then it would be t squared plus 2 times t plus 2 squared, which is, what, 4? Okay, so that's what I'm going to put up here. So I didn't know if y'all remembered anything about factoring cubes or not, so I figured that'd be a good one to go over. Most of the other ones there are a little easier. Okay, and then on the bottom I have t minus 2. Well, looky there. I get something that cancels out, right? So the t minus 2's cancel out. All right, so I have the limit of t approaches 2. My original function is going to be the same as taking the limit of this function, because they're the same except at that one point t equal 2, my original function didn't have a value because there would have been a hole in the graph there, but that's okay. I can proceed as if they're the same. And so all I got to do is plug this in to find the limit. So I'm just going to say, okay, it's t squared plus 2t plus 4. And I just got to plug in t is 2. Isn't this just PEMDAS again in evaluating expressions? You know? Some things never go away. It's what I've been trying to tell the 7th graders because they have such a hard time with PEMDAS and stuff like this. And it's like, guys, this is never going away. We got to get it. We can't just go, I'm not going to remember it the next time I see it. Because here it is again, and it just is always underneath everything. So this is going to be, what, 4 plus 4 plus 4? Which is what? 12? So the limit is 12. I could have put this on my calculator, and I could have looked at it. That's kind of hard to see sometimes what the y value is on the calculator, though, isn't it? You could use trace and kind of use that as a way to help you maybe. But this is how you could do it with algebra, is you just factor stuff out and cancel it out, okay? So I don't know if you had time to try number 13. We'll go through it together just to, if you haven't, you can just follow along and write down. But if you have, you can just check your work. All right. Now, 4 terms. Do y'all remember what that usually means I'm going to do? Yeah, factor by grouping, okay? So how you kind of look at it is we're going to group, if I do the top, let me group these 2 terms together, and then I'm going to group these 2 terms together and take out a GCF. We're going to have to do this on the top and the bottom, and I think this one you have to, if I remember correctly. Okay, so if I factor the first 2 terms, x cubed plus 2x squared, I can pull an x squared out of both of those terms, and what I'd have left over would be, what, x plus 2, right? And then I don't know if you remember this, but when you have a subtraction sign between the second and third term, you always factor out a negative, like a negative 1. Is there anything else that divides out of x and 2? No. So if I take the negative, I'm going to put a negative 1 here just because I'm going to need it here in a minute. That would just be x plus 2. And I go, oh, yay, look. This and this match. That's what we wanted to happen with factoring by grouping. So let me just go ahead and rewrite the top, and then we'll go look at the bottom. So if you remember, I factored now, I've got a new GCF. I created two terms, and they have a GCF of x plus 2. And my other factor is this x squared minus 1. I could keep factoring that a little bit more, couldn't I? Because don't we have a difference of two squares now? X squared minus 1 would be x plus 1, x minus 1. I'm running out of room, so I'll just stack it up here. Let's go look at the bottom now. I'll do that one in blue just to make it easier to follow. All right, so if I'm going to do the bottom, I'm going to group those two terms and these two terms. Out of x cubed plus 4x, what can I pull out? What would divide out of x cubed and 4x? Just x, So it would be x, and then inside I'm going to have, what, x squared plus 4? Okay.
Could you do x squared instead?
Oh, you're right. That is an x squared. Duh, x squared. You're right. Yep. Thanks. Yeah, it would be x squared, and then you'd have x plus 4, which is going to work out better, isn't it? If we don't do that, we're not going to have anything match. And then on the second set, you got an x and a 4. Nothing really divides out of those, but there's a subtraction sign between the second and third term. So let's factor out a negative 1. If I factor out a negative 1, doesn't that just change the sign on any term? So it would be plus x plus 4, right? So x plus 4. And I go, yay, because now they match. They wouldn't have matched had we not got that extra x out. So on the bottom, we have the x plus 4 that we can now factor out of the two new terms. And then we have what's left is x squared minus 1. Now, do you see how I went to the trouble to factor the x squared minus 1 on top? But did I really need to do that? No, because look, they're gone. So I actually could have not done that extra work there. That's one of the things about these that's kind of interesting is sometimes if you go all the way, it's not going to hurt, but, sometimes you do a little extra work. All right, so what I have left is something that I can stick this in, x plus 2 over x plus 4. So that's going to be plug in negative 1 on top, plug in negative 1 on bottom. And what would we get?
1/3.
1/3. There's my limit right there. Just think, if you'd had to go graph that, it'd have been a pain to graph, first of all. Even if you reduced it, it would have been a pain to graph. Now, if you typed it in on your calculator, it still would have been a pain to type in on the calculator, So sometimes algebraic ways just give us ways of dealing, I guess you pick what irritates you the least on these problems, as far as deciding how you're going to handle them. Okay, so according to the math police, we don't have radicals in the denominator, so life should be good. But what happens when I go plug in y equals 0 to the denominator? It becomes 0, which isn't helpful if we're trying to find the limit. So here's another technique that you can do. You've tried direct substitution. It didn't work. Here's what you can do, and it's really, kind of strange to think about it in a way because we've always been worried about our denominator, but what we're going to do is we're going to rationalize the numerator now. We're going to do the same process that we did when we rationalized the denominator. We're just going to do it to the numerator. And it's going to create an ugly looking thing, but it's going to be an ugly looking thing that we can actually evaluate. So what I'm going to multiply by is the square root of 5 plus y plus the square root of 5. It's the conjugate of the numerator this time. And we always worried about the denominator before. But now we're trying to get this, let's see if we can't rewrite it to make it work for us. And that's what calculus in a nutshell, that's what you spend a lot of your time in calculus doing, is rewriting stuff to get it in a form you can mess with. Usually it doesn't make it worse. Here it makes it look worse. But anyway, it's going to be helpful. All right, so let's keep writing limit as y approaches 0. On the top, I created a difference of two squares pattern, a squared minus b squared, because I have a minus b, a plus b. So my a squared would be the square root of 5 plus y squared. Isn't that just going to be 5 plus y? When you take the square root of something and you square it, you just get the same thing back. So in the numerator now I have 5 minus y Wait, that's a plus y. I can't even read my own writing. Okay, so I've got a squared minus b squared. I should write all that out and I'll be less confused. So a squared was 5 plus y minus b squared. Square root of 5 squared is just 5. And on the bottom, I got ugliness. I have this mess. I'm just going to rewrite it. Well, let's clean up the numerator. What is 5 plus y minus 5? Y. Ah. Oh, look, I got a y on the bottom, too. How's that going to be helpful? Yeah, they're going to cancel out. It's going to have a 1 on the top, and it'll have a 1 on the bottom, but it's gone away. So now I have 1 over square root of 5 plus y plus the square root of 5. And that I can stick this 0 into. That's the whole point of this, is I'm still trying to use direct substitution, but if I can just mess with this equation a little bit, use some math to rewrite it, I can stick this in now, because if I stick the 0 in, I have the square root of 5 plus 0 plus the square root of 5. Well, that's just the square root of 5 plus the square root of 5 on the bottom. Now, here's where I can combine radicals. If I have a square root of 5 and somebody gives me another square root of 5, how many square roots of 5 do I have? 2. Yeah. And we would just, now, here's one thing you're going to find. We're just going to leave our answer like that. You kind of had it drilled in your head that it's always bad to have a radical in the denominator, but in calculus, because we spend so much time doing this other junk, a lot of times if we get a radical in the denominator, we are perfectly fine with it, and we just leave it that way. And the answer key will even leave it that way, which is weird. I could rationalize this and write what that would be, square root of 5 over 10, but most of the time you just leave your answer this way. So you spend less time messing with your answer to get it in a form that matches the key, and you spend more time working on equations to get them where you can actually plug numbers in, at least for limits. There will be time we will do this. You'll see as if you're taking calculus, we'll go through the year, there'll be a time or two we'll have to do this throughout the year as we're messing with the functions.